So in this presentation, I introduce you software architectures. So the outline of the presentation, so we will start with the what software architecture is. Then we continue with the language through which you can specify your software architectures. After that, I will introduce you my own language, which is XCD for specifying software architectures. Last, I conclude with the current research conducted by our research group about software architecture. So let's start. So let's start with the motivation behind software architectures. Why we are interested in software architectures, or why the community of software engineering is interested in software architectures. First of all, software architecture is one of the most important topics in software engineering. If you are planning to do a career in software engineering or do research on it, you must learn it. You must learn how to specify the architecture of your software system. This is a must thing, you must learn it. It has already entered the field in the 90s through the American scientists. So nowadays it has been taught and researched in many universities. There are many research groups around the world that do research, that do active research on software architectures. There are many European Union research projects that do some innovative research on software architecture. There are also several conferences conducted annually that do research on software architectures and publish research-related papers. Yeah. Another thing is even the industry already adopts software architectures. There is a role called software architect. There is a role called software architect in which you do some software architecture specification for the software systems of that company and analyze it. Yeah. So let's now focus on the definition of the architecture in the most basic sense. What's architecture? According to the Oxford Dictionary, architecture is the art or practice of designing and constructing buildings. Another definition is the complex or careful design structure of something. So here the keywords are designing and constructing, complex and structure, which you will better understand shortly. Yeah? So let's have a look at some nice architectures, some nice buildings. So there are so many nice buildings around the world. Yeah? These are just 3 of them. So once people come across these buildings, what they say is what a nice architecture is. They directly point out the architecture thing. Yeah? They directly point out these architecture of these buildings. Yeah. So how such nice buildings are constructed? How such nice buildings are built? Is it that simple to build these buildings by gathering together masons, carpenters, or painters? Do you think is it that simple? No, of course not that easy. You need much more than these people to build such complex architectures. You can gather together these people to build small houses or just a wall of a big building, big nice building. But if you need some complex architecture, some nice building, you need the architectures involved in the construction. Yeah, architecture must involve in every phase of the construction if you want to build something nice, something complex. Yeah. So building nice architecture consists of the following steps. First, the architects design the building, draw up a plan of the building. Yeah, they decide how many people will use this building, what the purpose of this building is, which facilities people perform through these buildings. So architects design the building by considering all these constraints. Yeah, architects also consider what the quality properties as well. The building should be safe so that it can last as many years as possible. Yeah, that's imperative. Yeah. So once the architect draw up the building, what happens is the communication iteration starts between architects and the clients. Architects should go until the clients are happy with the architecture. Once the clients are happy with what has already been drawn by the architects, then the architects give the architecture to the constructor, to the painters, to the masons, who will realize it, who will build the buildings according to what has already been specified by the architects. Yeah? So here, architects still involved in the construction phase as well, so as to ensure that the building is constructed according to the architecture in a precise way. Yeah? So then the end result is a nice building itself. So that's how the nice buildings, the nice architectures are constructed. Architectures are involved in their construction. That's what I try to point out here, yeah? So, the same applies in software engineering as well. The same applies to the development of large and complex software systems. You can build small software systems without considering their architecture at all. But if you want to build something complex, if you want to develop some large and complex software systems that consist of several components interacting with each other through complex interaction mechanisms, then what you need to do is, first of all, consider its architecture and analyze it, identify errors, then proceed with the implementation. You cannot build large complex systems without considering their architecture. You can gather the best programmers around the world, yeah, who can produce very nice code, but it doesn't matter, it doesn't work. These programmers will not be able to understand the overall structure of the system and the constraints imposed on this overall structure without the architecture. The programmers need the architecture to understand what? To understand the components composing the system and also the constraints imposed on their interaction. Programmers cannot understand this without specifying the architecture, without having the architecture in their hand, so they cannot build large and complex systems then. So let's focus on what? The development phases of software system development in terms of architecture. So firstly, the software architect involved in the development phase, yeah? Software architect first provide what? Provide the software architecture specification, which is a composition of a system components through some interaction mechanisms, yeah? Once this has been specified, once this architecture of the software system has been specified, then you need to analyze that software architecture. Your goal is not just to enhance the communication by drawing some diagrams, some software architecture diagrams. Your main goal here is to analyze your software architecture, analyze your design, identify the problems early on, yeah? So once you have the software architecture specification, then the software architect or the software designer has to analyze it through some methods such as formal verification, which I will elaborate shortly. Then once you are happy with your architecture specification, once you decide that there is no any design error exposed through my architecture, you give that architecture to whom? To the programmers, yeah? Who will implement the architecture? Who will realize the architecture? Who will who will develop the application according to what has already been specified in the software architecture document, yeah? So that's how large and complex software systems developed. You have to consider their architecture first, then proceed with the implementation. So let's now have a look at the definition, the formal definition of software architectures. So David Garland and Mary Shaw, these two people are the founders of software architectures who works in Carnegie Mellon University in USA. So according to them, software architecture is to do with the structural issues in systems, yeah, in software systems. So what are those structural issues? They are gross organization, global control structure, protocols for communication between system components, synchronization between these components, data access, functionality of these components, distribution, composition of these components into a successful system, scaling and performance, and such quality properties. So I can summarize this definition as follows. Software architecture to me is a high-level design activity, a high-level software design activity for specifying systems as a composition of components in a way that meets the functional and non-functional properties of that system. So software architecture is just a way of specifying your system in terms of components interacting each other through some connectors, through some protocols, yeah? That's what software architecture basically is, yeah? So, there's a nice video I want you to have a look at about software architectures.
Great gigabytes into the software running up. My business is crippled. Thank you, sir. Remove that menu at once.
Sir, the system is failing because of poor planning. We need architects.
What I need is a system that supports my business.
That's why you need architects. Come with me.
Where are we?
This is the environment of the business you're conducting. And this behemoth is the system you're constructing. Your developers are working hard. But sir, it's up to you to provide the right support.
Hey, it's the guy with the tattoo.
Sir, pay attention, please.
I have responsibilities.
The first of which is to this crew.
But what am I supposed to do?
We have no right to help us see.
We're lacking in security.
Some headroom so that we can stand.
We need some tools. We need a plan. Oh, dear.
Sir, let me introduce you to the three architects.
architects. The enterprise architect,
Hello.
the solution architect,
How you doing?
and the infrastructure architect.
Sure.
Or in this world, a town planner, a building architect, and a utilities planner.
Right, nice job.
Why do I need architects?
Well, your building does not fit here, sir. Just have a look around. You're throwing off the balance of this peaceful little town, yes? These tools are insufficient for the job at hand. Listen to this lady, sir, and get yourself a plan, please.
Your elevator goes up but not down. The building's so thin it makes me frown. The passageways are much too small. By the way, your building's gonna fall.
Your electrical is all amok. You faucets but no aqueduct. Your entrance is a traffic jam, my good man. You need a plan.
I should say so.
Now you have a plan, now you have an architect.
Now you'd better pay attention. This is vital, I suspect.
Like a building or a city, every system needs a plan. Architecture designs the model and puts control into your hands.
I like it.
So what do you think? Can this system be built?
To better harmonize with this pastoral spread, your skyscraper will be an office park instead. Look, see. We'll provide your team with tools so they can work unstressed. I'll let my fellow architects explain the rest. Please go, please, please.
Your elevator now moves both ways. We've opened up the passageways. See? Wide enough to move around. Your buildings, all structurally sound.
Pipes for water, electric tools. Your team can see they won't do. Your road is wider than before. My friends, I think we have the cure.
That's it, Fatma. You've done it.
Now you have a plan, now you have an architect. Now your business is supported.
Your developers content, like a building or a city.
Yes. So, we now introduce you what software architecture is in the most basic sense. Yeah. So now it's time to understand. It's time to go through some methods, some language for specifying software architecture. Just like you need some language to implement your software, you need some language to specify the architecture of your software system as well. The most commonly known language is Unified Modeling Language. Unified Modeling Language gives you several kinds of diagrams through which you can specify your software architecture at different levels of abstraction. Yeah. So you will learn UML in your third year. So UML gives you tools, some diagrams through which you can specify your system in terms of components interacting with each other through some connector, through some communication mechanisms. Yeah. However, UML has a number of problems. First of all, it's weak in terms of its notation. Its notation is imprecise. Through using UML, you cannot always express what you intended to do. Yeah? What you produce as a UML diagram might be interpreted differently among different people. That's the biggest problem that the UML suffers from. Yeah? First, for example, let's have a look at this diagram. So as you see here, there are two clients. There are two client components requesting the service of a server component. Yeah? So these two clients use the service provided by the server. However, here, this diagram solely produced by UML. So I use UML to draw this diagram. But here, once I give this diagram to my programmers, I am the designer, once I give this diagram to my programmers might not understand some more detailed issues, such as that. These clients, in which order these clients request the service of the server? Who will initialize or instantiate this server? Who will initiate the connection with the server? So such kind of details are impossible to specify using UML. That's the problem of UML. So what happens is that my programmer will either redesign what has already been done to understand the communication mechanism, the communication protocols, or make some assumption which might lead to wrong results. Yeah? Another way of specifying software architectures is architecture description language. Yeah? There are so many architecture description languages that have been developed since the 90s. These architecture description languages are different from UML in the sense that they are precise. Yeah? They do not lead to wrong interpretations. Yeah? And also these architecture description languages offer facilities such as architectural analysis, early code generation. As you see, this is the table which includes my analysis of more than 20 different architectural description languages. So to read about my analysis, there is a paper accessible from my website. So in this table, we analyze more than 20 different architecture description languages in terms of different issues, which I will mention shortly. So these languages, architecture description languages, unlike UML, are textual. They are not visual. You cannot use this language to produce diagrams of software architectures. Yeah? So what you can produce using these languages is textual specification of software architectures, textual specification of components, textual specification of connectors that connect components together, yeah? So, however, there is one more very important characteristics of architecture description language, which I already mentioned. That's architectural analysis. UML doesn't let you analyze your software architecture. First of all, UML is imprecise anyway. But using architecture description language, you can analyze what you specify as a software architecture. You can understand design, you can detect design errors early on at the stage of software design. These design errors might be incompatible components or wrongly functioning components, wrong interaction protocols that are followed by these components in their interactions. So without architectural analysis, software failures become more likely. Indeed, there are several examples of software failures, which is due to the fact that these softwares haven't been analyzed during their design, during their architecture specification. Through architectural analysis, what you could do is you can do exhaustive testing. Architectural analysis allows you to do exhaustive testing. Exhaustive testing means that you can check all possible behaviors of system components. You can check all possible behaviors of interaction protocols between these components. That's why architectural analysis is very important. But in software testing, you can only check a single path of execution. You cannot go through all possible combinations of system component behaviors. That's why architectural analysis is extremely important. For instance, there are three kinds of examples. I put here the pictures. So TERAC, for instance, I would like to mention. TERAC is a radiation therapy system which has failed due to a software error. Yeah, this system failed, and TERAC, as a radiation therapy system, just exposed overdose radiation to the patients and caused a number of people to kill, a number of people to die. Yeah, just because software failure. So they haven't managed to find out all the mistakes before they release the software. So you can understand as much mistakes as possible if you analyze your architectural analysis, if you analyze your software architecture. That's why it's very important to analyze software architecture. And architecture description language gives you this opportunity to do so, yeah? So there's a little comparison between UML and architecture description language. First of all, architecture description languages are textual, which means that they are not so easy to use and easy to learn. On the other hand, architecture description language is offered with some precise notation. They do not lead to different interpretations. And most importantly, architecture description language allows you to analyze your software architecture. Nonetheless, there is also some problem. There are also a number of problems about architecture description language, just like UML has their own problem. So architecture description languages, unfortunately, are not popular. Architecture description languages haven't managed to enter the mainstream of practitioners. In industry, people still use unified modeling language to specify software architectures, despite the fact that UML leads to different interpretations. So architecture description language nowadays just used by research people for research purposes. That's the biggest problem of architecture description language. This chart has been produced by Malolta et al. As a result of some survey conducted among 45 different companies. So according to this survey, UML is used much more than the total usage of architecture description language, which is worth to investigate. Given that architecture description language allow you to analyze your software architecture, it's worth to investigate why they are not used by industry, by companies. So, according to our analysis, there is no architecture description language that doesn't suffer from either of the following problems. First of all, architecture description languages are textual. So they cause steep learning curve, yeah? Another problem is architecture description language hinders the reusability of software architectures and cause potential unrealizability. I will explain each of these problems shortly. So let's start with steep learning curve. So architecture description language, to be able to support architectural analysis, they base their notation on process algebra. Process algebra is completely new to the practitioners, new to the industry. It requires a completely different way of thinking. It requires you to consider your system in terms of processes concurrently interacting with each other. That's why people feel quite unfamiliar with architecture description language. Their notations are algebraic, which is found unfamiliar by practitioners. Yet practitioners always used to use UML, which is just the diagrams. So if you just provide them with an algebraic notation that's based on some mathematical concepts, nobody will use it, of course, yeah? That's the first problem that we identified. The second problem is that there are architecture description languages that do support connectors. There are also those that do not support connectors. So the architecture description languages that do not support connectors view software architectures in terms of component only. So using these languages, you can specify your software architecture in terms of components interacting with each other through some links. But how about complex communication mechanisms? What if I want to specify the protocols of communication between these components? In that case, you will need to embed these communication protocols as part of components. So each component has their own protocols of communication. However, this will make this component protocol dependent. You will not be able to use the same component in different contexts requiring different interaction protocols. So you reduce the reusability of the component. You will not be able to reuse the same component in a different configuration that requires different protocols of interaction. The last problem is unrealizability. So unrealizability means that once you specify software architecture, you may not be able to, the programmers may not be able to implement that software architecture in the way you specify. For instance, your client might ask you to specify a house or build a house that can fly. Yeah? As an architect, you can specify, you can draw a plan of such a house, but the builders, the painters, the masons, the carpenters will not be able to realize this building. Will not be able to construct this building. It's impossible unless you specify how you are going to make it fly. For instance, here as you see in the top figure, there is a flying house. In the bottom figure, the flying house is supplemented with two components that carry the flying house, yeah? So this is how you can specify how we are going to make it fly, yeah? But you ask your implementer, you just give your implementer the top figure, and expect the implementer to do what? To implement the system. It's impossible. The implementer is going to change your system as follows. The implementer needs to add some extra components to your system. They will not be able to implement what you have already specified without adding some extra components. They must add some extra component to make the house fly. So that's the biggest problem of architecture description language. They cause specifications that may not always be implemented in reality, yeah? So, to better understand this, to better understand the issue of unrealizability, let's focus on a real system, a nuclear power plant system. So this nuclear power plant system, there's a nuclear power plant system here specified. This system consists of 4 different components interacting with each other, as you see in the top figure. So there are 2 clients here, P1 and P2, and 2 servers, Na and Ur. Na represents here the nitric acid amount, while Ur represents here the uranium amount. So these clients access these amounts and updates them. However, here there is such a global protocol, global interaction protocol, that these Na and Ur amounts uranium and nitric acid amounts must always be the same at any time. So these P1 and P2 clients perform their update operation in a way that these amounts, Na and Ur amounts, are always the same. Yeah, there's such a global interaction protocol here that needs to be followed by these components in their interaction. So this global interaction protocol is specified in terms of message sequence charts given in the middle. One can easily specify a connector using the existing architecture description language, and this connector imposes this global interaction protocol. The bottom connector specification is specified using one of the most popular architecture description languages. There's a glue element, as you realize, in this connector specification. This glue element states the global interaction protocol that I just mentioned. However, they haven't described how the components is going to satisfy that interaction protocol. They just describe the interaction protocol itself without describing how that operation will be performed. So that's why using this language, you have the potential unrealizability problem, yeah? So we produce, in London, we produce a new language. We design and implement a new language called XCD. XCD addresses these three problems. XCD aims at enhancing reusability and making the language more user-friendly and guarantees realizability of software architectures, which I will mention shortly. Yeah? So, XCD is reusability. Reusability is very important. Reusability is the most important design principles of software systems. You have to make sure that you design your software system by reusing what has already been done. That's how you can reduce the cost of developing software systems and enhance the quality of software systems. You have to increase reusability as much as possible throughout every single phase of software development. That's the main goal of software development. So, XCD considers reusability as something very serious. To this end, what we've done is we offer two separate components, two separate elements of XCD. These are components and connectors. So designers, architects specify their architectures in terms of components interacting with each other through some connectors, yeah? So components. Components in XCD are specified in terms of data and some ports. Data represents the state of the component. Component is just, by the way, a computational unit, a unit that performs some operation, a unit that receives some data, makes some calculation, produce some output, just like methods in C, just like classes in Java, yeah? So, the components has their own ports as well. It is through the ports that the components interact with their environment. So components use their ports to send or receive messages to their environment, yeah? Ports can be either event ports or method ports. Through event ports, what you do is send asynchronous events to outside or receive events from outside. Method ports is used to send method calls, and here you need to wait until you receive the response. That's how method calls differ from event ports. In method ports, you have to wait until you receive the response. Connectors. So connectors are the units of complex interaction mechanisms. They are used to specify the protocols of communication between the components interacting with each other, yeah? Connectors includes a role definition for each component participating to that connector interaction. Connectors have some parameters as well. It is through the parameters you pass components, interacting components to the connectors and make them interact with each other through some protocols. So connectors apply protocols to the components through its parameters. Connectors receive components through its parameters and associate each component with its roles and make them obey some interaction protocol. So XCD also is not algebraic, unlike other architecture description languages. XCD is based on a completely different, much more user-friendly notation, which is offered with design by contract approach. So in XCD, the behaviors of software modules, components, or connectors are specified in terms of contracts. Yeah? Contracts is what? Contract is just an agreement between the user of that software component and the producer of that software component. So for that software component to operate properly, both the user and the producer of that software component must obey some rules, some constraints. Preconditions are the rules that needs to be obeyed by the client of that component, by the user of that component. Post-condition are the rules, the conditions that needs to be met by whom? By the supplier, producer of that component, yeah? Just like Java methods or C methods. Once you use a method from the library of C, you have to make sure that you put the correct parameters to that method, yeah? That's the precondition. If you do not put the correct parameters, then that method will not be able to work properly, will not be able to work as intended. Once you put the parameters correctly, this means that precondition is satisfied. You as a client perform the satisfy the precondition, then the method itself guarantees you that, the developer of the method itself guarantees you that the method produce the correct result. Yeah, this is the post condition. This is what the developer of the method needs to obey. Once you give the correct parameters, the developer of the method guarantees you that the result will be correct as well. So that's what contract is basically. So we apply contracts to the specification of components and connectors. The methods and events of component ports are specified in terms of two types of contracts. These are interaction contracts and functional contracts. So each event, each methods are attached with two types of contracts. Here, interaction contracts represents when that method can be called, when that method can be operated, when, for instance, here in the screen you will see a server port. Server port includes a single method called request method. There are two different types of contracts attached, interaction contract and functional contract. Here, interaction contract states that the request method can be offered to the component environment only when the initialized data of the component is true. Once you offer your component, once you offer your method to the component environment, then the functional contracts comes into the stage. Functional contracts update the state in the way specified. Their responsibility is to change the component state after you perform the method operation. Yeah? So realizability, we already handled realizability in XCD. We guarantee realizable specification. So any architecture specification described using XCD are guaranteed to be implemented in the same way they are specified. So if you need further information, there's a paper that describes how we ensure realizability. Yes, another important thing is XCD supports formula analysis automatically. So you can analyze your XCD architectures automatically. Yeah? By doing so, you can identify a number of design errors, which I listed here, such as wrong use of component services, wrong functional behaviors of components, wrong interaction protocols of connectors, and so on and so forth. So to do so, what we've done is we produce some compilers. We produce some compilers that translates any XCD architecture specification into process algebra models. Because these process algebra models are supported with analysis tools, once our translation once our compiler perform the translation from XCD to process algebra, then designers can use these analysis tools to perform their architectural analysis, to identify the mistakes in their software architectures. We later on do the same for a separate process algebra. So we provide two different compilers that produce two different process algebraic models, because each process algebraic model has their own analysis tools, some of which is more powerful than the others. Having done that, we analyzed, we evaluated our approach, we evaluated our compilers and also the language syntax semantics itself in terms of several real system case studies, such as Aegis Combat System, gas station, lunar lander, English auction, and what? Nuclear power plant system. Yes, so we have a group, we have a research group that has just been established in our university, and this research group just focuses on improving XCD nowadays. So now our main focus is to improve this language to a further point. What we are doing currently is we are producing a GUI editor. So using this GUI editor, software architectures can be specified visually as well. So currently, the XCD only offers textual notation, but our group now works on building some new set of notations through which designers can specify their software architecture visually. Yeah. So to do so, we already constructed two different teams. that work closer to each other. The first team builds the architecture diagram editor itself, and the other team works on the compilers. So the compilers here are used for the purpose of translating any visual notation, any visual specification into textual specification, and vice versa as well. Because that's how we can make architectural specification, visual specification analyzable. Yeah, currently we only support the analysis of textual notation. That's why we need compilers. We need to translate any XCD visual specification into textual specification. That's why we need compilers. Yeah. So that's what we are doing currently in university. Yes, questions? Yeah, I finished early. Yeah. Do you have any questions? Of course you have. Soru var mı arkadaşlar? Any question you have? Don't be shy. Yes, Hamza.
How do you show
The synchronization. Say how we satisfy synchronization. Yes, synchronization is outside the scope of XCD, but synchronization is quite important in the sense that if you are working on a concurrent system, you must make sure that the components of these systems synchronize with each other properly. But XCD focus more on the distributed systems, not their concurrency itself. So synchronization is completely about concurrency, which is outside our scope currently. But we can improve XCD in the future to support synchronization as well, to support the synchronous communication of components. Just like what? DNA, yes.
Yeah, actually, I guess that biological mathematics is used in that way. So
Yes, exactly. Yes, yeah. To some sense, what you said is sensible. Yeah, I mean, we make people. Yes, exactly. We make people specify their architecture in terms of components interacting with each other through some connectors. Yes, we have some components, we have some elements, just like existing in DNA. Yeah, that's a good approach. Yeah. Yes. Yes.
Do you think that when these kind of creators become common in the software, it will be drop UML?
That's our goal. I mean, that's the goal. That's what we aim to do. I mean, by developing graphical user interface for our language, our goal is to attract the attention of industry. Our goal is to make industry use our language. That's our precise goal here. I mean, that's why we intend to enhance the usability of our language by making it visual, because we know that people use UML, which is visual. Yeah. But that's just the goal. There's of course no 100% guarantee that they will just shift UML from our language. But that's just a hope. Yeah. So any other questions? No question? Oh, that's it. Huh?
uygulamalı daha çok zor oluyor yaparken.
Evet.
Anlamasını anlıyoruz.
Evet. Uygulamasını da yaparız bir ara. Tamam o zaman. Bitirelim arkadaşlar o zaman. Tamam.
Teşekkürler.